So I want to talk about one of the most recent results that we have. So Rudi talked about all the difficult stuff that we had to do. And the good thing is that at a certain point you can harvest all the results. So this stuff comes relatively easy after the hard work that Rudi does, that he presented. And this talk will follow roughly the same pattern, where as soon as it gets difficult, I will refer back to Rudi's talk and say, well, he explained all this, so I don't have to do that. So my talk is about symmetry in matroids, but I want to start off with symmetry in graphs for two reasons, basically. The first is that it's just a very nice result, so it may serve as a nice warm-up. The second is that then the topic of my talk lines up pretty well with the title of the workshop, which would then be Symmetry in Graphs and Matroids. So suppose that we have a graph here. I want to talk about automorphisms of this graph. So an automorphism is a permutation of the vertices such that whenever uv is an edge, its image under this permutation is an edge, and the other way around. And we say that the graph is symmetric if the only automorphism that is possible is the trivial one, the one that keeps every vertex in place. And there's a nice theorem here that says that almost every graph, so if the number of vertices tends to infinity, almost every graph has an automorphism group that is trivial. So almost every graph is symmetric. And the proof is pretty nice. So suppose that we have a random graph where every edge is present with probability 1/2. Then for any possible automorphism, you can look at the probability that this automorphism is actually an automorphism of the graph. So for example, the probability that the automorphism swapping 1 and 2 is actually an automorphism in this graph. Well, look at the neighbors of this vertex 1 in the graph on top. So 1, 2 is an automorphism precisely when 2 has the same neighbors as 1 has. And this edge may or may not be there, this edge 1, 2. So that way you can compute the probability that this is actually an automorphism of the graph. And you can do that for every candidate automorphism that you may be interested in. And by summing up all these probabilities, you get a very nice upper bound, which proves the theorem over there. So this is just for graphs. What I want to do is talk about matroids. So we have a notion of automorphism in matroids, where we again have a permutation, which is now a permutation of the ground set, where any set is a basis if and only if its image under pi is a basis. And again, we call a matroid symmetric if the trivial automorphism is the only one. So this is from the same paper that Rudi mentioned, the Mayhew, Newman, Welsh, and Whittle paper. And one of the conjectures there is that almost every matroid has no non-trivial automorphism. So almost every matroid is symmetric. And using our techniques, we can get pretty close to that. So we're not quite there yet, but we get pretty close in two ways, actually. So the first is that we can prove that almost every matroid, it may be asymmetric, but if it's asymmetric, then it's asymmetric in a very specific way, namely, we can swap two elements and that's it. The second is that if we restrict ourselves to the class of sparse paving matroids, then the conjecture holds. All right, so I'm going to need some stuff about the Johnson graph. Well, you've all heard the definition of the Johnson graph. Here's the nice picture again. And actually what we're going to use is that the circuit hyperplanes of the matroid form a stable set in this Johnson graph. So that's sort of a weaker statement than what Rudi talked about, where sparse paving matroids are precisely the stable sets in the Johnson graph. Here we are just concerned with circuit hyperplanes. So the proof goes roughly as follows. So suppose that we have a candidate automorphism pi, and this is indeed an automorphism of the matroid M. If that is the case, then the circuit hyperplanes are pi invariant. Every circuit hyperplane is mapped to a circuit hyperplane. And since the circuit hyperplanes are stable sets in the Johnson graph, it follows that the circuit hyperplanes are precisely a pi invariant stable set in the Johnson graph. So here's our goal for this talk. We want to show that the number of pi invariant stable sets of the Johnson graph is very small. And then we can use one of the general theorems that we proved. So I will not explain what it means exactly. I will just refer back to Rudi's talk. So it says that if we have a class of matroids and the number of circuit hyperplanes that appear there are very small, there's a very small number of possible circuit hyperplanes, then the class is necessarily small. So we want to talk about pi invariant stable sets. So let's take any pi invariant stable set right here. And suppose that we pick a vertex, so this one. Then since the stable set is pi invariant, if I take the pi image of this vertex, then it must be in the same graph. Then it must be in the same stable set. So it might be the vertex over there. And then if I take the pi image of that one, it must still be in the stable set, so it may be that one over there. And at a certain point, I completed a circle, and I have a nice circuit in my stable set. This is called an orbit. So this is sort of standard terminology in group theory, I guess. So this is an orbit, and if you keep repeating this, then you find that you can actually partition the stable set into pi orbits. So the things on the right are sort of special. You can have orbits of size 1 where the vertex is mapped to itself by this automorphism. Okay, so what we want to show is that the number of possible pi invariant stable sets is very small. And we want to have a sort of concise description of such a stable set, as Rudi mentioned, is basically our main trick. So what can we do? Well, if we pick a vertex from each of these orbits and we close this set under pi images, and we get back the whole stable set. So that's what we're going to do. We want to describe the stable set by picking a subset, then closing under pi images, and that gives a short description. Now there are a couple of cases that we want to consider. The first one is perhaps the easiest, where you have many large orbits. And an orbit for me is large if there are at least 2 vertices in it. So suppose that we have at least capital lambda large orbits, then, well, I can pick any vertex in each of these orbits, and whatever choice I make will give me the same stable set if I close under pi images. So that is naturally upper bounded by the number of stable sets in the Johnson graph divided by 3 to the power lambda. 3 because in every one of these orbits I can take one vertex or the other vertex or both vertices. And that's sort of the worst case if you have a large orbit consisting only of 2 vertices. Well, if you pick this capital lambda as something like a constant times the logarithm of the number of sparse paving matroids, then the upper bound becomes exponentially smaller than the number of sparse paving matroids. And this would be sufficient to plug into our general theorem and give the result we want, at least when there are many large orbits. So of course, we have to work a bit harder when there are few large orbits. Then we cannot do this nice trick. But of course, when there are a few large orbits, then we can just pick one element from each of these orbits, which forms a small stable set, and there cannot be too many small stable sets. But then you're sort of left with the fixed points on the right of this graph. Right? There can still be many of these. So we have to fix that somehow. So here's again, it's a pretty general lemma that follows from our methods, actually from the Scythe method, which states that if we want to bound the number of stable sets of a particular size, then, well, it says it right there, you get an exponentially smaller bound than the number of sparse paving matroids. So the first of these factors on the right works for us. We still have to work for the second factor. So we want to bound the number of fixed vertices, stable sets consisting of fixed vertices. Okay, this may be the most technical slide in my slide deck today. So we start out a little bit simple, perhaps. If you have a permutation, there is something called the disjoint cycle notation, which says that, well, you can describe this whole permutation by just giving the cycles of it. So this means that 1 is mapped to 5, which is mapped to 8, and 8 is mapped back to 1. The same for 2 and 3, which are swapped in any application of this permutation. So these give cycles gamma 1 up to gamma m, and we write capital L for the cardinality of the support of this permutation, so the number of elements that get moved. Now suppose that X is a vertex of my Johnson graph that's fixed under this permutation pi. Then each of these cycles is either contained in X or it's completely disjoint from X. This means that for every such vertex that's fixed under pi, we can sort of write down the signature of this vertex, which is then just the set of all indices of cycles that are fully contained in the vertex. And then for each possible signature, we can look at the Johnson graph that's induced by this signature, by which I mean that we look at all the vertices that contain the right cycles and avoid the wrong cycles. And the induced subgraph is isomorphic to a smaller Johnson graph. So the Johnson graph is smaller in two ways. There's n minus L, so L was the support of pi. And you can see that because for all of these L elements, you say, well, they either have to be in my set or they are not there. So these are specified, so that explains the minus L. And there's some R prime, which is the size of these sets. And that depends a bit on which cycles exactly are selected. In any case, as these signatures sort of partition the stable sets in the Johnson graph, or partition the Johnson graph, then we can just take the products over all possible signatures over the stable sets in this smaller Johnson graph. And then if you plug in the right bounds, you find something like sparse paving matroids on a smaller graph, on a smaller set, to some power, where the 2 to the m is just a number of subsets of cycles that you can have. Okay, so if the L, the number of points that get moved by this permutation, if that is at least 3, then we find a nice bound on this int fixed, the fixed vertex stable sets in our graph. And that L at least 3 kind of explains why our method doesn't give anything better than either your trivial or you swap exactly 2 elements. All right, so what did we do? We have this large Johnson graph. We have a stable set there. If there are many large orbits in this stable set, then we're done. We can just select subsets. If there are few large orbits, then, well, the large orbits are not very interesting because there's just few of them. And the Singleton orbits we can handle as well. Provided, again, that the length of the support is at least 3. So that gives the first of our theorems. And now in order to prove the case where you have two elements that get swapped, so the case that's still annoying us a little bit, we want to assume that we are working with a sparse paving matroid. So okay, now we're working with a sparse paving matroid, and we have a transposition, so a permutation that swaps two elements. And this is the lemma that we can show. It says that the number of stable sets that are invariant under this swapping business is bounded by the number of stable sets times a factor. And the factor is very small. If R is typical, so R is a half n roughly, then it says something like n squared divided by 2 to the n. So this is a very small factor, and as a result we get that sparse paving matroids that are invariant under such a transposition is small compared to the number of sparse paving matroids. Right? So the proof is relatively easy. So if you have a stable set in a Johnson graph that is pi invariant under this specific pi, so this is the Johnson graph, and the thing on the top right says that these are my vertices that contain E but not F. Right? So the labels indicate the intersection with the set E and F. So if you have a stable set in the top right, then it cannot be pi invariant. Because if that happens, then its pi image would be in the stable set as well, and the pi image is obtained by swapping E and F. So it's a neighbor in the Johnson graph. So that cannot happen. So you're in these two blue areas. And then we can construct a stable set that's not pi invariant by just adding a point there, which can be done in this many ways, and then removing its neighbors. And then the R times n minus R you get back by sort of trying to reconstruct a neighborhood, which is easy because it's a stable set. And these neighborhoods are cliques. So that solves our problem for sparse paving matroids. And we're left with a conjecture that if you just look at transpositions, then the matroids that have just one transposition, that's a very small class. I'm sort of running out of time, so let me just show you one thing. So these are the upper and lower bounds on the number of matroids that Rudi showed in his talk. We can show that the limit of this transposition business, well, we don't know what it is, but we can show that if it exists, then it must be 0, which is good. And we can also show that if the limit is not equal to 0, then the upper and lower bound on the number of matroids are essentially the best possible. We cannot improve these constants 1 and 2, which I think is a bit weird if that would happen. So my money would be on this limit exists and is equal to 0. All right. So there are a bunch of open questions. I will just put them on the board here. And thank you for your attention.
Any questions? Peter?
Is your money on the 1, the 2, or somewhere in between?
That varies by day, actually. So the question is my money on the 1 or the 2 or something in between? I don't know. I really don't know. I would like to know very much. Yeah, it really varies by day, which I believe. James.
What do you think the situation is for binary matroids?
So the question is, what would the situation be for binary matroids?
Yeah, almost all binary matroids asymmetric.
I believe that's the theorem. There's an asymptotic formula for the number of binary codes, which implies that almost every binary code is asymmetric by y.
So Dylan is referring to a paper by Marcel Wild, that is, I think, right? He enumerated binary matroids, and it would follow from his result that almost all binary matroids are symmetric. Yeah, that sounds good. Thanks, Dylan.
I think we had one more question at the back there. No?
I did see one hand.
Yeah.
Yeah.
James asked, I was going to ask about representative.
Ah, well.
Any other questions? No? Well, we'll just set up for our next talk now.